So I want you to keep thinking about the fact that Lenz's law opposes you. And you can think about that in very direct ways. So for example, I don't need to keep going back to the flux and the current and all that. I can simply say, oh, if I'm moving a magnet towards a coil, if the North Pole is approaching, Lenz's law says that the current in the coil sets up a system that opposes the change. If the North Pole is approaching, what kind of magnetic pole will stop that? So the current in the coil will set up a system where it creates a North Pole to oppose me. If I try and pull a North Pole away, the current in the coil that I induce will set up a magnetic field that creates a South Pole to drag me back again. So very directly, you don't have to think about it, keep going back to first principles. You can just say, if I'm trying to do something, it's going to be directly opposed by effect of Lenz's law. And here's some videos. They're long, I'm going to skip through them, but basically, these are on our website, and I want you to kind of like, I'm just going to show you bits. But it's really kind of startling, some of the things that happen because of this. So here's this very nice gentleman who's, I hope you can hear it, he's a very nice gentleman who's going to talk us through some stuff. And I'm going to jump around.
Show a couple magnetism demos over today, and these all have to do with Faraday's law, so the application of Faraday's law. So I want to show you this one here. We have coil, and we have an iron bar in there, which increases the magnetism that it can create. And we have the coil connected to AC power supply. So when I turn this on, what's going to happen is AC source is going to come through here. The AC current is constantly changing as a sine function. So that means the coil is going to create a magnetic field inside of it. And because the iron wire is there, it's even stronger. And that magnetic field is also going to be constantly changing. So when I put a ring here, turn this on, you see the effect there. If I put the ring like right now, the ring will levitate. So what's going to happen here is this one creates a changing magnetic field inside of this ring, and then there's a current induced in the ring which opposes the magnetic field that created it. So the current itself will create its own magnetic field, and the two will repel each other, pull each other.
So can you see, that's Lenz's law. That's causing levitation. You know, it's basically, oh, you want to make a North Pole? I'll make a South Pole. Oh, you make a South Pole? I'll make a North Pole. Oh, I'm sorry. You want to increase your North Pole? I'll make a North Pole to keep you away. It pushes away. Oh, you want to make a South Pole? I'll make a South Pole to push you away. And it causes this thing. Watch what happens when you stop the current from flowing in the ring.
So a mechanism that you can see, that you could use as levitation. And if you keep it there for a while, you come and touch it, it's already warmer, okay? Now if I put this ring, I always show this to my students. I put this ring and nothing happens to it, so I say, what happened? And they're just thinking, and then they see that it's actually doesn't make a closed loop, so you can't have a current in here. So it's not just sufficient that this be a metallic ring, but it needs to be a closed ring. So if I put it, nothing happens.
So I want to just jump around a bit because I ain't got time to show it all. So let's have a look. Yes, I'll do that. So this is the bit where we're talking about a. So now, well, actually, no, I don't want to show that because that's not Lenz's law. Oh, I didn't mean to do that. Let's have a look. I want to go. Yes.
Is something like this. We have two tubes, okay, and we have two similar looking objects here, these blue looking objects here, and I'm going to drop these objects through these tubes, and we're going to time how long it takes each one, see which one goes there faster. So as you drop it, you see one of them goes really fast, takes
Not so
much
fast.
longer. Okay? So there's that levitation effect. So what happened? Well, this one went a lot slower. And what you learn is that this is actually a magnet. So if you put it something metallic, okay? You see, like here I'm putting it against this metal, this sticks. Whereas if you put this, it doesn't stick at all, right? So this is a magnet. So the magnet, when I'm dropping it here, I'll try it again here. You can see it's going really slow.
So what happens here is that as the magnet is, let's say you're a piece of the metal in the pipe, as the magnet's approaching you with its north pole, it induces a current in you, but because of Lenz's law, you say, oh, absolutely not, that north pole is approaching, I'm going to create a north pole that will keep it out. And so this thing takes an age to work its way through the pipe. And there's nothing holding it back. It's not that it's a tight fit. There's no trick. It's just the induced current opposes the change. So, and on the back side, as your south pole is leaving, it says, oh, a south pole's leaving me. Absolutely not. I'm going to make myself a north pole to bring you back. So both above and below, it's fighting the change. And I want to show you this next bit, which is this next one, which is, so this is actually what? This is Stanford, I think it is. Berkeley, sorry. That's a coil.
One of the first ones was professors here went to the World's Fair in November 1920.
And that's a pan that is 3-4 inches off the coil.
This aluminum dish was turned specifically. The dimensions are very exact. Well, they were at one point. Yeah, it's a little lopsided, and it should sit about here. And you can actually demonstrate these.
The neighbors complain. So again, very interesting effects. We've got one of those. We got a means of transportation that does that very close to here, maybe 50 miles away. Anybody know what that is? You might have ridden on it if you took your kids or you went as a kid.
The monorail in Disney World.
Not the monorail, but and Futureland. You know the little blue trolley system that takes you around on the second floor?
Oh yeah, the World of Tomorrow.
Yeah, World of Tomorrow, yeah. That's a maglev system. That's one of it. Like, my brother sat on that in 1981, electrical engineer, and he was thrilled. He was like, this is amazing, you know. And now it's like, because we've progressed so much further. But, you know, that's a situation that particular, I don't know if it's still there, but that attraction has, is that, you know, Tomorrowland is to some extent, that, you know, yesterday's land, because we're changing so quickly. So those are those two. Let's get out of here, and let me see if I can get back to my presentation, and we'll continue. So from current slide, yeah. Okay. So Lenz's law opposes you. So let's just look at some examples of this. So we have a bar magnet. Oh, I'm sorry. Every time I come back, I've got to reset my pen. So. Yeah. So when we come, so we have a bar magnet. North pole is approaching. North pole is approaching. What it's going to do, I'm going to, well, let's think of it from a flux point of view. From a flux point of view, when I'm a long way away, I have very few flux lines going in. So this is, you've got to be real careful about perspective here. I am looking from that side. There's my eye looking in that direction. And I am seeing these arrows going away from me, and two of them are going through the loop. And then as the magnet gets closer, more of them go through the loop. If that happens in time, did I induce an EMF? Yes. Faraday's law says I induced an EMF. What did I do in terms of my flux? I increased the amount of flux going into the loop. Agreed? Everybody comfortable on that? Looking from the side, if I had 1, 2, 3, 4, I'm going to move my loop rather than anything else. Initially, my loop was like there, and only 2 of them went through. That was my first diagram. And then I said move my magnet, but I could just as easily move my loop. And now 4 of them are going through there. So I literally increased the flux going through my loop. Agreed? Increase the flux causes an EMF. EMF causes a current flow. Current flow is in a direction to directly oppose what I just did. So what happens is that my current flow is such that my system says, oh, absolutely no, pal. You had 2 of these guys, and that's all you're going to be left with. So I'm going to create that guy, and I'm going to create that guy, and I'm going to cancel out those 2 that you added. Now, here's my wire. That's that guy. And here's my magnetic field going round. And I say, if the current's flowing upwards, the magnetic field goes into the page on that side and out of the page on that side. Here, I want it coming out of the page, so yes, my current flow goes like that. Down here it goes like that. Let's go through that again. I'm looking here. I want to create this black coming out of the page. If my current's flowing up by my right-hand corkscrew rule, it goes into the page on that side and out of the page on that side. Agreed? And I want it to be out of the page to the left of the wire. So that tells me the sense or the direction of the current flow. There is an easier way. And that is this. Again, I'm looking at this coil in that direction. I have a north pole that's approaching. What will the coil do to try and keep the north pole away? Creates a north pole. Right N, put the little arrowheads on. Isn't that the same answer? Here I had the current going in a counterclockwise direction, and here I have the current going in a counterclockwise direction. One's from first principles, one's from the pragmatic approach of whatever you try and do. Lenz's law says I'm going to try and oppose you. So let's play with this a bit. A bar magnet is dropped with its north pole pointing downwards. It is moving on axis towards the horizontal loop of wire, as seen from above. I've got to tell you, as seen from in these. As seen from above, what sense, clockwise or counterclockwise, will the induced current have in the wire loop? So, north pole is approaching. What will you do to try and keep the north pole away? You create a north pole. And so as you look from above, it's counterclockwise. I think every example I've given so far has been counterclockwise. Okay, let's do a couple more. Oh, this is, so no, I don't want to do that yet. Let's just do a couple more. Let's reinforce this. I'm going to pull that guy away. What will this coil, what will this loop do to try and stop this change? North pole leaving would be going to be attracted back by a south pole. Put the south in, put the arrowheads on. Oh, that's a clockwise motion, clockwise current. South pole approaches. The coil says, I don't want that south pole to approach. I'm going to create a south pole to keep you away. There's my direction of my current. Okay? Now, it gets a bit tricky sometimes, so I'm going to erase one of these. I'm going to erase that guy. Because, if I ever can get that thing to work. Let's stick with this second diagram. Here's my loop still. Imagine that I actually dropped this so that it was leaving. So I actually dropped this all the way through. When the south pole was approaching, I created a south pole on the north face of this to keep the thing away. When it's fallen through, the north pole is leaving. So how will the current flow? Yeah. Let's step through this. I'm going to look from the side. I'm going to create a south pole here, aren't I? To keep this guy back. Agreed? If I have a south pole on that side, I've got to have a north pole on that side. Yeah? Because they come in pairs, yeah? So that means, oh, okay. As looking from above, I have a north pole, not the south pole. So you've got to be careful on these about looking from which direction. If I had looked at this not from above and had the magnet pulling away, if I had looked at it from underneath and had the magnet pulling, can you see the difference between my two perspectives? You get the same current flow, but it looks clockwise in one sense and anti-clockwise in the other sense. So your perspective really matters on this, and that's what can catch people out. This is another class of examples. I just want to see how I'm doing. Yeah, okay. This is another class of examples. So this is a solenoid. And I have a magnet approaching. Now, notice, let's just talk about the solenoid to begin with. A solenoid is a helix of wire. That's a solenoid. That's a solenoid. Well, it's got to be connected to a circuit. That gets connected at that side. Connected at that side. They're not the same. In this case, my solenoid is going up and around and around and around and around. And in this case, it's going up the back and that way and that way and that way and that way. They've got a different winding sense. And that changes it. Not to mention, they're also solenoids. And I can wind it that way, or I can wind it that way. So with these diagrams, you've got to pay attention. You can't just say solenoid and I'm off. You've got to look at how it is wound and everything. So you've got to be careful about that. I'll leave those there for a minute. This says a bar magnet. Oh, sorry, didn't mean to do that. Wrong way. This says a bar magnet is pushed to the right with its south pole pointing to the right. It's pushed towards a solenoid along an axis of the solenoid. As viewed from the left, what pole will be created at the left end of the solenoid here? Oh, okay. So if I look from the left, I see that. and this wire is on that side. Can you see that? If I'm looking at this guy from the left-hand side, I not only can see the circle, but I can see this wire, because that's going to come into it. I am having a south pole go towards this, so what pole will this create to keep me out? South. Now, with your sense of traffic, if I'm going round a circle like this, which way will the current flow in this wire? Will it be up or will it be down? Down. So we say, as viewed from the left, what pole will be created at the left-hand side? That's the south. Now I've got to erase these guys. In which way will the induced current flow through the resistor? So now I'm looking and I'm saying, okay, we said down, which means it's going that way, which means it's going X to Y. I'm going to change this question slightly. I'm going to say, as viewed from the right, which pole will be created at the right end? So now, the magnet is still at the far end, and it's still as south, and it's still inducing a south at the far end. But at this other end, if the south is at the far end, this end is a north. Yes? Now, looking at this, looking at that way, here's the kind of weird thing. It's the same picture. It's a bit odd, two ends, when you turn it around it looks the same. There's a north pole at this end, which means that my current is going up, which means that it's going in that direction, which means it's X to Y. That has to be the same answer, doesn't it? That doesn't depend on perspective. That's a reality. So there's some practice on the homework. One of these is going to be on you. There's something on Lenz's law is going to be on the test. And this is a very nice conceptual structure. There's 4 different permutations of the solenoid I can do. I can have the magnet coming or leaving. Or I can even do, and this fair game, I can even do this. Oops, I didn't mean to do that at all. Click on that. In fact, but it's actually, that's a useful, I'm glad I saw that, because let's go here. I can even do this. I can do I can say, give you a second just to finish the diagram off. I can say, when I close the switch, what way will the current flow in this guy? So I'm closing the switch, and the current is flowing in that direction, agreed? Yeah? And that is creating a south pole, which is getting stronger because I closed the switch. The current is going up. Which means there's a north pole here, which is getting stronger. Which is like a north pole approaching. Which is going to be met by a north pole there to try and keep me away. Which is going to cause the current to flow up that wire, which means the current flows from Y to X, from y to x, yes, y to x. So I close the switch, and because of the science of this diagram here, I know this is the positive end, so my current flows upwards. I know because it's wrapped that way that it's the south pole. I know it's getting stronger because I close the switch. If a south pole is here, an increasing north pole is there, which is like bringing a north pole towards it. Lenz's law tells me I have a north pole to oppose it. Again, because of my sense, I know that the current's flowing in that direction, so it must go from y to x. That's also a question. So play with these. There's going to be something like this on the test, so play with it. Almost done. These last two bits, we kind of wave goodbye to before we do spring break, basically. So basically, induced EMF and electric fields, we consider a ring of uniform magnetic field that changes in time. So the magnetic field is changing in time. The work done in moving a test charge once around work is equal to Q times the EMF. Work done in electric force is Q times E times the path difference, which is 2 pi r. We equate these two guys together, so Q times my EMF equals Q times my electric field times 2 pi r. So my E is equal to my EMF, my electric field is equal to EMF over 2 pi r. And if I remember that my EMF is equal to minus d phi by dt, then I get my electric field is equal to my EMF over 2 pi r, which equals minus d phi by dt over 2 pi r. And that gives me the electric field times 2 pi r. Electric field times 2 pi r is equal to minus d phi b by dt. So the integral of E dot ds is equal to minus d phi b by dt. This means that the induced electric field is non-conservative, that the line integration of E dot ds is not 0. And frankly, I don't do anything with it. So I want you to know it's there, but it's not like you got 5 homework questions based on it and all that kind of stuff. I'm usually rushing at this point. That's one thing to know about. I suppose our usual thing is know that the equation exists. You don't need to remember it for the test. You don't need to remember it for the test. And know what the symbols stand for. And then Maxwell's Lorentz. And so this again is something for your, to know it's there, but we've already done some of this in quite fine detail. We did this guy, didn't we? Whose law is this? It's most of the law. There's a bit missing, but whose law is that? Good old Gauss. And then when we did magnetic Gauss, we did that bit, but there wasn't much we could do with it because it equals 0, yeah. And then we did the generalized form of Faraday's law, which we just introduced. And then we say, all right, the line integral of magnetic field around any closed path is the sum of mu naught times the net current through the path, and epsilon naught mu naught times the rate of change of the electric flux through any surface bounded by that path. So we get this expression. And again, I don't do anything with this. I'd like you to know it exists and the like. And then the final little bit is Lorentz force equation, which says, well, force, we have the charge being affected by an electric field plus the charge being affected by the magnetic field. So. And then we kind of have it. So it's a good way to end for the break.